Hi everybody, a very quick little video just overviewing how to calculate the fundamental frequency for a pipe that is open at one end and closed on the other, just like we did in class today. So right here I have a pipe that's open at one end and closed on the other, filled with air. The gas that's inside the pipe is very important. Since what is vibrating is not the actual pipe but the air inside the pipe, it's very important to use the velocity of sound in whatever gas at whatever temperature is inside the pipe. It's a little hard to picture because with a string you can see it waving, but inside a pipe you have the air sloshing back and forth and creating essentially a standing wave of longitudinal air vibrations. And those vibrations are what create the fundamental and the higher harmonic frequencies. So it's very important to use the wave speed, and in this case we're always talking about sound waves in the air or whatever gas is inside the pipe. Okay, so what note will it play? Let's say I happen to have a tube and the tube is, I don't know, let's say it has a length of about 30 centimeters, which is 0.3 meters. So, you know, a reasonable size length, about as tall as a 2-liter Coca-Cola bottle, but a cylindrical tube. And we want to like know if I blow across the top, what is the fundamental frequency of the sound that will come out of that tube? Okay, so let's figure it out. And the most important thing that you need to remember, other than we have air inside the pipe, and we can assume for this problem it's room temperature air. If it's not room temperature air, you'll be told otherwise. We know the velocity of the sound wave in that case is going to be approximately 343 meters per second. So we know the velocity. We want the note, so we want the frequency, but in order to get the frequency, we need the wavelength. That's where we have to come back to our length-wavelength relationship, which, if you recall, for an open-closed pipe, is that the pipe length supports a quarter of a wave when the air is vibrating in the fundamental mode. So if that's the case, let's come and do our calculation. 0.3 meters is a quarter lambda, and that means lambda is 0.3 times 4, which is 1.2 meters. Now it's really hard to picture this wave, and that's because I haven't actually shown you an animation of what's going on inside the pipe to create this wave. There's some interesting pictures in your reading, and if we have a little time next class, I'll show you a quick animation. It's a little hard to, even with the animation, it's a little hard to picture, but it might help you to at least get a sense of what's going on inside the pipe. So I know my wavelength, which is right here. I know my velocity, and then I told you this was the most important equation in this unit, and it's turning out to be true, right? So 343 meters per second equals frequency times 1.2 meters, and that means the fundamental frequency is 343 divided by 1.2, which is 285.8. Let's say 286 hertz. I feel like that's maybe around like an E or something like that, close to it. So that's our fundamental frequency. Now, what if I asked you, what's the frequency of the second harmonic? It's a trick question, right? Because sound waves in tubes only have odd harmonics. We saw from the sound spectrum it skips the even harmonics, and that's because of the asymmetry between the open and the closed end of the tube. So we don't have a second harmonic. So if I asked you what the second harmonic is, you'd say there is not one. But you can tell me the frequency of the third harmonic without doing any fancy calculations, just by remembering that any harmonic is always a multiple of the fundamental frequency. So if I take this and I multiply by 3, 286 times 3, I get 858. And then the next one, F5, would be 5F1, which would be 286 times 5, and I get 1,430 hertz. So you can always figure out the harmonic structure of the open-closed pipe, even though you can't really draw the waves easily. You can still imagine the structure and deduce it from that. So that's all I wanted to show you. Things to keep in mind. You're always going to be using the fundamental frequency, so you're starting with that L equals quarter wavelength to find the F1. It's always air or a gas inside the tube, so you're going to need to use the known speed of sound in the material at the temperature that's inside the tube. And it will be different if you're not at room temperature. It will be different, as you'll see, if it's not air. And then you're always coming back to your tried and true wave equation over here. I hope this is helpful just to give you a review of what we did today, and let me know if you have any questions on the assignment. See you later. Bye.